Welcome to Lecture 4 of Algorithms. So today we're going to talk about a concept called recurrence relations. And to introduce that concept, we're going to give our first example of a recursive algorithm. Recurrence relations are sort of the fundamental mathematical object that we can use to analyze recursive algorithms. So, let's start building some intuition by thinking about a really simple recursive algorithm. So, many of you should know the concept of factorial. Right, so factorial is defined as the following. So I write n with the exclamation point, and that's read n factorial, and that means the product of all the natural numbers n and lower. Right, so that means 1 times 2 times 3 times ... times n minus 1 times n. Right. So one of the nice things about factorial, and this is a basic mathematical idea, basic mathematical concept, and it's it's used as an example of kind of how we can apply recursive algorithms in a really simple way. So one of the ways of writing n factorial is recursively. So I can write n factorial as n times n minus 1 factorial. Right? Why is that? Well, let's just look at the formula up above. So if I take n factorial, I can break that down into the product of the first n minus 1 integers and n. Right? So this piece here, the first piece, this is just n minus 1 factorial. Right? Times n. Right? So this is one way of thinking about n factorial. Is n factorial can be defined as n times n minus 1 factorial. Okay, and then, to be very clear, we have to make sure that we define 0 factorial as 1. Okay, so 0 factorial is defined to be 1. And I'll use the colon equals to say that's a definition. Right, and if I have this thing put together, that's actually a complete recursive definition of factorial. So let's use that recursive definition to build a recursive algorithm for computing n factorial. So here's how it will go. We'll call this algorithm f. So f of n is supposed to return the factorial of n. Right, so it's defined like this. First, we'll take the starting condition here. So if n equals 0, then what do? We return 1. Otherwise, what do? We return n times n minus 1 passed to this algorithm. Right? So we return a recursive call on n minus 1. So else we return n times f of n minus 1. Okay, fair. It shouldn't be too hard to convince yourself that this particular definition, this recursive definition of an algorithm, will return n factorial. Right? If I pass in a number n, it'll just recurse on itself till it gets all the way down to the initial condition 0, and then it'll bubble back up and send us the product of all those numbers. Okay, so this is one algorithm for computing factorial. Now, one of the pieces of our program when we're analyzing algorithms is always to identify a basic operation. Right? So our question here can be, what's the basic operation? And here it's worth thinking about this as our basic operation. Right? In particular, thinking about the product. All right, so in order to analyze this algorithm, let's write an expression that captures the number of multiplications that are performed to compute n factorial. So our basic operation is going to be times, right? It's going to be multiplication, and so let's let t of n be the number of multiplications that we have to perform to compute the factorial of n using this algorithm. Okay, so this is number of mults this algorithm performs. specifically when we give it an input of n. So on input n. Okay. So we want to come up with the number of multiplications as a function of the number that we pass to it. Okay. And we're not asking in general, we're asking this algorithm. All right. So let's think about this. So what is t of n, right? How can we express t of n here? Well, suppose I want to understand t of n, but I don't want to analyze the whole thing, and I just want to come up with an expression that captures what t of n is. I could do it like this. I could say, look, I don't know what t of n is, but I know that unless n is 0, it's going to have at least one multiplication. Right? If I am trying to come up with an expression for t of n, one thing I know for sure is that as my algorithm executes, unless n is 0, I'll get to this line, and this line has one multiplication in it, right? So I know that there's at least one multiplication. Who knows how many more it takes, right? But I know there's at least one, and then perhaps more, right? And so what does perhaps more mean? Well, it means I'm going to add on however many multiplications I get from this function call. Okay, how many multiplications do I get from this function call? I don't know, however many multiplications I get when I pass n minus 1 to the function. So what do I get? T of n minus 1. Okay, so this thing here is called a recurrence relation. Recurrence relation. Just rel, right? And we're going to get really comfortable with analyzing these things, but let me make sure that it's absolutely clear what this is capturing. Okay, so what this captures is the following. This says we will always have at least one multiplication when we run this code. Okay, certainly at least one multiplication. One multiplication, right? Where does that multiplication come from? It comes from right here, right? That's our multiplication that one is capturing, okay? And then there might be more, right? I don't know. I'm not going to go count them, but I'm going to let my recurrence deal with it, right? And so what this says is maybe there's more, right? In fact, I'm just going to say there's as many more as there would be if I passed n minus 1 to my function, right? And so what this says is, we know that there's one, and that's what the one here is saying, but then there are as many more as there would be if we pass n minus 1 to the function, right? And so then this is as many more as there would be if we pass in n minus 1 on an execution of the function f of n minus 1. And where does that come from? That comes from right here. Right? That's this piece. The piece that says, there's more calls of this thing, right? We're gonna call the function again. That'll result in more multiplications. I don't know how many more. I'll let the recursion deal with that. Right? So a recurrence relation is just an implicit way of defining the running time of an algorithm. Okay, so t of n means here's how many multiplications it takes to compute n factorial. I know that it's at least 1, plus however many it takes to compute n minus 1 factorial. Okay, and notice that this isn't quite complete, right? Because we also need to include our base case, our recursion base case in this. So we need to include the stopping criterion. What's our stopping criterion? Well, it's t of 0 equals 0. Okay, what does this mean? Okay, so the function t means the number of multiplications we perform to compute factorial of the argument. How many multiplications do we perform to compute the factorial of 0? Well, we compute no multiplications, right? If we pass in 0, no multiplications occur. Okay, so this is 0 multiplications. 0 mults, which is why we have a zero here. Okay. So how do we analyze this? So we have this thing all put together, right? We've got this t of n equals 1 plus t of n minus 1, and t of 0 equals 0. Right? This is a completely well-defined recurrence relation that describes a function. But how do we analyze?